Algebra 2 Honors 10.2 Day 1 Notes. So we are going to be looking at independent and dependent events and some formulas for their probabilities. And so determining whether events are independent. Two events are independent when the occurrence of one does not affect the occurrence of the other event. Very typically, that's if we have different items in a bag and we grab one and then we replace it before we grab another one. So it's as that second time we go to grab something, it's starting just like it did for the first time. And or if I have one die and I roll it once and observe the number, and then I roll it again and observe the number, events on each of those are independent of one another because the second time I rolled it, I started with the same possibilities as I did the first. So anyways, there's a formula that you need to know. And so two probability of independent events, two events A and B are independent if and only if the probability that both events occur is the product of the probabilities of the events. You need to know this formula. Need to know this formula. And so determine whether events are independent. They want you to show that the probabilities fit this formula, and the product of probability of A and B is equal to probability of A times probability of B. They want you to use this formula. So let's see what that looks like. A quiz is student takes a quiz randomly, guesses the answers to 4 true-false questions. Guesses is so that each getting true or false was equally likely. There's no knowledge, really. Use a sample space to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. Well, question 1 and question 2 correctly, that's fitting this probability of A and B. So we're letting event A is you get question 1 correct, and event B is you get question 2 correct. And so the probability that they both occur, A and B, so you're getting both question 1 and question 2 correct, these will be shown to be independent if that probability is equal to the probability of their individual multiplied. So, I'm going to work on the right-hand side here first, and I'm going to highlight some things in the chart. A is the event of getting question 1 correct. And getting question 1 correct, it doesn't mean correct only. It's just any time you see in the first letter that it is correct, in that first question it was answered correctly, we've got to take it. It doesn't matter what else happened. So I see correct here, correct in the first position, correct in the first position, in all of those. Doesn't matter what happens after, but in all of those, the first answer was correct. And so there was a total of 16 in here, and I just highlighted 8 of them. So the probability that the first question was answered correctly was 8 out of 16. All right, so then I'm going to go through and erase those, and I'm going to go to the probability of B. In probability, I'm going to highlight any question where the second is correct. So there's where the second's correct, second, and second, and count those up. Again, that was 8. So there were 8 out of the 16 where the second question was answered correctly. On the left-hand side, I need to go through and highlight where both the first and the second were correct. So I'm looking through and I'm trying to see where I have the first and the second correct. And anytime I see the first and the second correct, I'm highlighting it. And that Probability was 4 out of 16. And so 4 out of 16 reduces to 1/4. This is a 1/2 times a 1/2. 1/4 equals 1/4. And since it makes that formula true, that is for independent events, they are independent events. All right, and so an extra example number 1, a bag contains 6 pieces of paper, numbered 1 through 6. A student randomly selects a piece of paper, replaces it, and randomly selects another piece. So again, since they are replacing those numbers, that means that when you go to get the second piece of paper, you have the same likelihood as you did the first. And so I expect these to be independent, and I'm going to show it by using this formula: probability of A and B equals probability of A times probability of B. And so I need to kind of look at the sample space. And this is kind of a big sample space because there's 6 numbers on the first, 6 on the other, and there's a total of 36 possible outcomes. So if I think about a tree diagram, I've got 1, 2, 3, 4, 5, 6, and then out of each end, I have 6. So it keeps on going. So I've got a 1 followed by a 1 followed by a 2, 1 followed by a 3, 1 followed by a 4, 1 followed by a 5, 1 followed by a 6. I have a 2 followed by a 1, a 2 followed by a 2, a 2 followed by a 3, a 2 followed by a 4, a 2 followed by a 5, a 2 followed by a... It's basically the same kind of setup that we had when we rolled the 2 dice. You get a 3 and a 1, a 3 and a... 2, a 3 and a 3, a 3 and a 4, a 3 and a 5, a 3 and a 6, 4 and a 1, 4 and a 2, 4 and a 3, 4 and a 4, 4 and then a 5, 4 and then a 6, 5 and a 1, 5 and a 2, 5, 3, 5, 4, 5, 5, 5, 6, and 6. Oh boy, that's my sample space. And so it says, use a sample space to determine whether randomly selecting a 5 first and randomly selecting an odd number second are independent. Well, randomly selecting a 5 first, so I'm going to let that be event A. And event B is going to be an odd number second. And so if I look at this set of outcomes, the probability that I get a 5 first is this row right here. And that's 6 out of 36. And then the probability of getting an odd second, to be kind of careful here, an odd second is this column, and this column. Even though I'm just in a column, this whole thing, right? The second number is odd. Same thing here, the second number is odd. Same thing here, the second number is odd. So that's half of the 36. So it's 18 out of 36 times that happens. And then if I can erase that without erasing everything else, that's the right-hand side. Now, on the left-hand side, probability of A and B, where 5 is first and the odd is second, well, that's fewer cases. 5 is first and odd is second are only those 3 cases. So the probability of that happening is 3 out of 36. So I expect them to be independent. Do they reduce to the same? This is a 1/12. This is a 1/6 times a 1/2. And yes, 1/12 equals 1/12. They are independent. It's important that you show details like this and that you label what you're letting be event A and event B, and then I can see all the individual probabilities as you show. So part of this is you're going to have to remember the process. It says, use a sample space to determine whether randomly selecting a 5 first and randomly selecting an odd number second are independent events. This is the process we're looking for. Example 2. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So I'm overall trying to go the probability of randomly selecting a girl first and a girl second is the same of taking the product of you getting a girl first times getting a girl second. So in this, if I look at the chart, the probability of getting a girl first, well, a girl first is all of those and all of those. And so that is 9 out of 12. There's a total of 12 there. Count them up. There's 6, 6. There's a total of 12. And in 9 of those, they have a girl first. All right. So then if I look at the probability of getting a girl second, well, getting a girl second are those 6 out of 12. So that is 6 out of 12. And then on the left-hand side, where in here do I have a girl first and a girl second? Well, wherever I have a girl first and second are all of these. And that is 6 out of 12. And I have a 1/2 equaling 3/4 times 1/2. 1/2 does not equal 3/8. They are not. Oops. Oh, you know what? I have to go back and edit this. The girl second, I lost some. Oh, that was bad. I have to go back. Sorry. This girl second, I missed all of those. So the girl second is actually, you're probably wondering what I was doing there, is 9 out of 12. And this is then 3 out of 4. And this is 9 out of 16. Oops, almost missed that. And so anyways, they do not come out the same. And they are not independent. And part of this is implied by they chose a student to be a speaker. And when they choose a different student to be a recorder, you're not choosing from the same pool of people because you've already taken one out who's a speaker. That by default makes it dependent, and I didn't expect this to work. Okay, finding probabilities of events. In example 1, it makes sense the events are independent because the second guess should not be affected by the first. In example 2, however, the one that we just looked at, the selection of the second person depends on the selection of the first because the same person cannot be selected twice. These events are called dependent events. Events are dependent when the occurrence of one event does affect the occurrence. Independent, they don't. Dependent, the occurrence of one event affects the occurrence of the other. And the probability that the event B occurs given that the event A has occurred is called a conditional probability. So it's the probability of B given that A has occurred, and it's written like this. So you see the probability of B, that slash thing, but it's vertical, and an A after. That is implying that event A occurred. Now what is the probability of B? And if the events are dependent, the fact that A happened will change the probability of B. This is called conditional probability. So, in words, if two events A and B are dependent events, then the probability that both events occur is the product of the probability of the first event and the conditional probability of the second event. So here are the symbols. You need to know this formula. And so if we look at using the information example 2, the probability that the girl is first was 9 out of 16. And then the probability that the girl was second, given the girl was first, would be 6 out of 9. Right here, given that the girl's first, when you see this given, you only look at those where the girl was first. And if I go back up here and I look at the ones where the girl's first, there's this many and this many. And I eliminate those so there's not as many in the pool. And so there's 9, a total of 9 in that. So that's my denominator right here. And then of those, you look where the girl is second. So of that set of 9, how many have the girl second as well? And so if I go up here and I look out of that set, how many have the girl second? 6 of those 9. And so that is that numerator. So that probability that the girl is second, given that the girl is first, is calculated differently than what we did before. And in that way, it does equal the 1/2, which we get in example 2. All right, find the probability of independent events. As part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. Well, first of all, I would identify these as being independent, because it doesn't matter what I spin on the first. Every number on the second spin has the same probability as it did the first time I spun it. And so anyways, I'm looking for, let A be the getting a 5. And I'm letting event B get a number greater than 3 on the second spin. And so I'm expecting these are independent so that I can go right to that independent formula to calculate these. And so to get the probability of 5 on the first and a number greater than 3 on the second, I can just go, getting a 5 on the first spin is 1/8. They're equal areas, equally likely to get each number. And then getting a number greater than 3, well, that would be a 4, 5, 6, 7, or 8, which is 5 out of 8 possibilities. And so we get 5 out of 64, which is about 0.078, or about 7.8%. So example 4. Find the probability of dependent events. A bag contains $20 bills and $500 bills. You randomly draw a bill from the bag, set it aside, and randomly draw another. So this is called drawing with no replacement. And when there's no replacement, we're going to be choosing dependent events. Because there is no replacement, that means there's fewer to pick from on your second pick. So that means your first event affects the second. And that's why we're going to choose dependent probability. So we have event A defined, event B defined. So the probability of A and B occurring should be the probability of A, and then it's the probability of B, though it is given that A has occurred. And so the probability you get, the first is 100 and the second, you have to think, oh, okay, how many bills are there? There to start 20 and 5, so there's 25 you're choosing from, and how many of those are hundreds? There are 5, so you have 5 chances out of 25 to get the first 100 bill. Now on the second, given that you got 100 on the first try and you did not replace it, that means there's now only 24 bills in the bag, and not only that, there are only 400s left because you picked 100 on the first try. So that gives you 20, or actually if you reduce that, you get a 1/6 times a 1/5 is a 1 out of 30, which is about 0.033 or 3.3%. So typically give the fraction, the decimal, and the percent. So another example like this, there's 9 women and 6 men on a committee. 2 people are randomly chosen from the committee members to serve as a chairperson and a treasurer. Chairperson is chosen first. Find the probability that both events A and B will occur. So A, the chairperson is a man, and B, the treasurer is a woman. So probability of A and B happening, it makes a difference because you're first picking out of 15 and then one person is gone, so the second time you're only picking out of 14, so event A definitely affects the probability of event B. So we're going to choose dependent events, and when that happens, we're going to get the probability of A times the probability of B, given that A has occurred. And the probability that the chairperson is a man, there are 6 people out of a total of 15. And then on the second one, you one person's gone from the selection, so there's only 14. And the second is that the treasurer is a woman. Well, you didn't pick any women the first time, so there's still 9 women left over. And so this is 3/5 times I don't think I did this right. So, just in my pre-done notes, I think I messed up. I mean, those values are okay, but I'm just checking something out. Oh, yeah. So the 6 and the 14, 2 goes into those, so it's 3 and 7, and then 9 and 15, 3 goes in each of those, 3 and 5, and so we've got a total of 9 out of 35. And that's good, and that's about 0.257 as a decimal, or about 25.7%. So that's it.